will share, because some assignments will be given to you. You have to also submit the assignments. It will be better to use the Google Classroom for the first this 1 month that you are doing online classes. Uh, okay. So I think it's visible. Please, you can write in the chat. Is it visible? My screen is visible or not?
Yes, sir, the screen is visible.
Okay, thank you. So we'll start with some basic definition. The first is you will face these terms like network analysis or circuit analysis, circuit theory. All these terms will be used. Here you will have a separate subject called network analysis, I think. Okay. In the book, you will get either circuit theory or circuit analysis. So, what is the basic definition between network and circuit? Because these two terms you will face repeatedly. So interconnection of two or more elements, if you see the first point, interconnection of two or more elements is called a network. Okay, this one. Interconnection of, it is called an electrical network. Just two or more elements connected with each other. Okay, there are some other definition of that also that we will also see. But it's just, if it's just connection between two or more circuit elements, be it active, passive, anything, it is called a electric network. If there is a closed path, if the network contains a closed path, that means a path through which current or charges can flow, or in other words, current can flow. Okay, that will become a electric circuit. Okay, if the network contains at least one closed path, there can be like open paths also, open interconnection of elements, but it should have at least one closed path for a network to become a electric circuit. So this is the basic definition between network and circuit. So this you can conclude that every circuit is a network. Okay? Every circuit is a network, but all networks are not circuit, because circuit will have some interconnection, and it should also have a closed path. So definitely, since it has interconnections, it will be a network, interconnections of different elements. But all networks are not circuits, because the closed path may not be available. So all networks are not circuits. Okay. Yes. Then it is linear and non-linear elements. Okay. So if you are applying some voltage, if you see the voltage and current relationship, if the voltage and current relationship is linear, if for a resistor, we'll see that for a resistor, you can see it's a linear. Okay, V and I. If this is the V, this is the I, you can see that the relation between V and I is linear. Okay. If this, again, for a diode, you know that it is a non-linear. Okay, so diode will be example of nonlinear element, and resistor, capacitor, inductor, all these will be a example of linear circuit element. Okay, so a nonlinear circuit is one. Uh, okay, so this is an example. These are the example of linear one, linear circuit elements. Okay, a semiconductor or diode operating in a curved region of the characteristics is a common example of a nonlinear element. Just okay. Then active passive. Okay, so any element that which is capable of increasing the level of the signal energy that is already present in the circuit, if some element can increase the level of the signal energy, then that will be known as active element. Okay, that will be known as active element. If it cannot, it will be known as passive element. So example of active element, any kind of sources, current and voltage source, again battery, BJTs, transistors, FETs, okay, and the kind of transistors, op amps. These are all treated as active elements. Passive elements, again, the usual suspects like the resistor, capacitor, inductor. Thermistor will come later. Okay? Thermistor will come later. So resistor, capacitor, inductors, they are termed as passive elements. If you have any doubt, you can unmute yourself, you can speak up, or you can write in the chat. I will periodically see your chat, and also you can just unmute yourself and ask questions. Okay. Then unilateral, very important, unilateral element and bilateral element. Okay, so let us say there is a resistor. Okay, there is a voltage source. There is a voltage source. So, so this is V, this is R. You can find out what is will be I. Okay, you'll be able to V equal to IR, Ohm's law, I equal to V by R. You can find out this. Okay, what happens if you change the polarity of the voltage source? That means here on this side there was plus minus. Now on this side you are making plus, this is minus. Then what will happen? Again, this is resistance value remains same, the voltage value remains same, only the polarities of the voltage source have changed. So what will happen to the this current will remain same, the value of the current will remain same. This I will be equal to V by R, but what will happen is it will flow in the opposite direction. Okay, so what are these unilateral elements? If you if this is, let us say this is element, we don't know whether this resistor is a unilateral or bilateral element. You are connecting it with a voltage source. Now when you complete the circuit, some current will flow. Okay, some current will flow. The current will have two things. The current will have magnitude and direction. Okay, for this, now you have reversed the polarity of the voltage source. Then in that case, if the magnitude of the current remains same, if the magnitude of the current remains same as before, but the direction can change. If the direction changes, okay, so if you reverse the polarity of the battery, the magnitude remains same, but only the direction has changed. In that case, that element will be a unilateral element. If, see the first, if the magnitude of the current flowing through a circuit element is affected when the polarity of the applied voltage is changed, the element okay is not affected, is not affected. This will be not affected. The magnitude remains same, the polarity may change. Okay, then that will be unilateral element. If the magnitude gets affected, then it will be a bilateral element. Sorry, that will be a unilateral element. Sorry, this resistor will be a bilateral element. Okay, if the magnitude it gets affected, that will be unilateral element. Okay, if we change the polarity of the applied voltage, the direction of the current is changed, but its magnitude is not affected, that will be a bilateral element. So the resistor will be a bilateral element. And diode, let us say, if you see this diode, again you are applying some voltage to it, you are applying some voltage to plus or minus. Okay, so it will be forward bias, so current will flow. But now the same, the diode polarity you are not changing, you are only changing the polarity of the battery. Now it is reverse biased RB, this is forward biased FB. So in RB it will not allow any current flow for the initial part. Until unless breakdown happens, it will not allow any current flow. So here let us say some current I was flowing, but when you have reversed the polarity and now the diode is in reverse bias, I is becomes equal to 0. The magnitude of the current has changed. So diode is an example of unilateral element. Whereas resistance, where only the polarity or the direction has changed, the magnitude remains same, that is the example of bilateral element. Okay, that is the example of bilateral element. Okay, yes, any doubt? Unilateral and bilateral element. Bilateral, even if you are changing the polarity, the magnitude of the current that was flowing, that remains same, only the direction changes. Unilateral, the magnitude of the current that was flowing initially, that changes when you change the polarity of the battery. That is the unilateral element. Okay, lumped and distributed element. Okay, lumped element, again, we whatever we'll be doing in this in this course, that will be all are lumped element. Okay, lumped element is the element which can be separated physically. That is resistor, inductor, capacitor. Okay, in a circuit, RLC circuit, let us say what you do. This is resistance, this is capacitor, then there is inductor. Okay, so each and every element that can be separated physically. So this is the resistance. If you are creating a circuit, if you are making a circuit on a breadboard, you take a discrete component, that is the resistance, then you take a capacitance, then you take a inductance L. So when they can be physically separated. Okay, Asutosh is saying, sir, in diode, the magnitude has changed from I to 0. So it should be bilateral. If we see the first point, if the magnitude of the current flowing, okay, if the magnitude of the current flowing through the circuit is affected, sorry, this will not be there. This not is not will not be there. Okay, is affected when the polarity of the applied voltage is changed. The element is a unilateral element. The magnitude gets affected when you change, then it is a unilateral element. So here for a diode, initially the current was I. Okay, when the diode was in forward bias condition, when you have made a reverse bias, that means you change the polarity. Okay, then the diode becomes in reverse bias, I becomes equal to 0. That means the current flowing to the circuit element has been affected, That's why it is a unilateral element. Okay, sorry, it's I made it not, so that's why the problem is. Okay. Yeah, lumped element means when like you can physically separate the resistor, inductor, or whatever components you are using. Okay, elements you are using, that you can separate physically. Okay, when you are creating the circuit, you are using a resistor separately, then you are using a capacitor, then using a inductor. Okay, if you can do that, that is a lumped element. So whatever analysis we will be doing, those are all for lumped element. Okay, distributed elements in your uh, third year. In your third year, you will study a subject called EMFT. Okay, electromagnetic field theory. So there is the concept of transmission line. Okay, in antennas and everything, there will be concept of transmission line. In transmission line, you cannot there. This transmission line has some properties of capacitor, it has some properties of inductor, it has some properties of resistor, but you cannot separate them physically. They will be distributed across throughout this whole transmission line. You cannot physically separate them. Okay, so so transmission line is an example of distributed element. Okay, so distributed elements are those which are not separable for analysis purpose. Example of distributed elements are transmission lines, in which the resistance, inductance, and capacitance are distributed along its length. Okay, if this is the length of the this transmission line, you cannot separate like where is the resistor, where is the capacitor, where is the valve. It is distributed throughout. If it's the length L, then throughout the length L, it will be distributed. All these properties, all these phenomena of capacitance, inductance, and resistance, it will be distributed throughout the transmission line. So that is an example of distributed. Whatever we will do in this subject, it will be lumped. Okay, we will be dealing with lumped elements. Active and passive. If a network contains at least one active element, we have already seen in our previous slide. That means you can any element that can uh, alter or increase the voltage level or signal level. Okay, that is a active element. So any circuit which have active element, that is a will be an active network. And if there is no active element in a network, that will be a passive network. That will be a passive network. So I have not given the this definition separately, since presence of active element will make a network active. Presence of this, if there is no active element present, that will be a passive network. That's why I have not written it separately. Time variant and time invariant. Okay, let us take a simple example for time variant. Again, in third year also you will face, before that also you will face this time variant and invariant. So let us say again the same example. That means there is a resistor, there is a voltage source. This R, this is V. So I will become equal to V by R. Okay. Now what we are considering, that this resistance remains constant. Okay. If you have if you have made the circuit, that means constantly currents are flowing, charges are flowing, and you will be getting some amount of current. Okay, but if you keep this circuit on for a sufficient amount of time, what happens, this resistance, the temperature of the resistance will start increasing. So temperature will temperature of the resistance will start increasing. Okay, it will start. As a result, what happens, the resistance, the actual resistance R, that will change. Okay, R, there is a relation, R is equal to R01 plus alpha delta T. Okay, this we will discuss in detail in our next subjects or instrumentation, because this property will be used by thermistor and everything. Okay, for making temperature measurements. Using the change in the resistance, it will try to give us an idea about how much temperature has changed. Okay, so this is the, let us say, some reference temperature, resistance at temperature 0 degrees C, or any room temperature, let us say. Okay, then if this much amount of temperature has increased, delta T degree centigrade, let us say, then the new resistance will be R. Now, if you see practically, this R will change over time. That means it will be RT. This R will change over. So the current will be V divided by RT. So this current will also become a function of time. Okay, so now see the definition. A network is said to be time invariant or fixed if its input output relationship does not change with time. So that means if you're considering an ideal resistance whose resistance value do not changes over time. Okay, it is not a function of time. Then the network, whatever network you are considering, where the input is V and the output is current I, then this network will be a time invariant network, because you have considered an ideal resistance whose resistance value doesn't change with increasing temperature. As a result, the I will always be V by R. But see the second point, the network is said to be time invariant if for any time shift in the input, an identical time shift occurs for the output. That means, let us say now, let us consider that R is a function of time. So if you are measuring, let us say at t equal to 0 degree, t equal to 0 second. That means just now we have switched on the circuit. That means the resistance have not heated up. Okay, but if you are measuring the current at a temperature at a time, let us say 5 seconds, that means some heating has happened. As a result, the resistance value has changed. You will get different input output relationship. So that will be a time variant. So this will be time invariant, this will be time variant, this will be time variant. If for any fixed time shift, the identical time shift, okay. In time variant, the input, sorry, this one, third point. This is time, this is okay. This is time invariant is okay. For time variant, the input output changes over time. That means IT becomes now, it is V divided by RT. As time changes, R changes, your I also changes. So for time variant network, input output changes with time. Time invariant, it remains constant. Now this is a property. The second point is a property of time invariant system that will come later. That will come later. It is a way of finding out whether a network is time invariant or invariant. Okay, I am teaching the same thing to the third year. That will come later. Okay, the second point you can skip. Okay, because for that other things need to be known. Only the first and second point is relevant to you. If the input output relation changes with time, it is a time variant. If the input output relation remains constant over time, that will be a time invariant. Okay. Yeah, till now. So we have done some basic definition. Circuit, network circuit, linear, non-linear, active, passive, unilateral, bilateral, lump distributed, active, passive network, time variant and time invariant network. So these basic definitions we have now done. Okay, here if you have any doubt, please let me know. Because any circuit will be given and a particular part, a particular problem there will be many subparts, A part, B part. So any circuit will be given, and you have to analyze that circuit. Okay, A part will be whether this circuit is active network or passive network. Okay, this can be given. These questions can be given. Okay, whether this particular element is a unilateral or bilateral element. Okay, this type of questions you can expect. So the understanding of this definition is very important. I will also share these slides. No issue. Next, we will go into this. First, let us consider these active elements. Okay, chat. Capacitor is time variant, but the its capacitance value, if it remains constant, if sorry, if C remains constant, if C remains constant, then it will be time invariant. C is equal to epsilon A by D. We will discuss in this detail. Epsilon A by D. If the cross-sectional area and the distance between the plates that remains constant, then capacitance will remain constant. RC circuit is time variant. Again, you have to see the response. You have to see the response of the circuit. Okay, that means for RC circuit, what is important? The tau, that the time constant. Okay, whether the time constant is changing over time or not. Yes, if you give a time varying voltage, it response will be something. But here the response is this tau. Okay, tau is some function of RC. Okay, if R is constant, C is constant, then the time constant is also, it doesn't vary with time. Okay, I'm talking about the response. Okay, that means input output relationship. If you RC circuit, if you only consider the output, if you only consider the output, that is time varying. But I am considering input output relation. That means you have to somehow get output divided by input. This kind of a relationship. That means both are changing over time, but the way that RC circuit is behaving, that will not change, because this if this R and C remains constant. Okay, if this R and C remains constant, then that is the case. Output is time varying. Output is time, but the response, that means relationship between input and output, that depends on RC. If R and C are time invariant elements, the value doesn't change over time, then the response will be time invariant. Okay, fundamental difference between input output relationship. The important word here is input output relationship. I am not talking about output. Output is time varying. That is, but how this output varies with input, both are time varying. Then what is the relationship between them? So first we will see some active elements. First we will see some active elements, and then different kinds of active elements. Again, diode and again transistor and all those things that will come into the second unit. The active elements that will be requiring for circuit analysis in this unit. Okay. Rest of the active elements we will see in the our next unit, and then we will move to resistance, inductor, capacitor. That means the passive elements. Sources. Uh, so broadly, we can classify the sources in two types. Okay, dependent source, independent source. Again, both again independent sources. So sources can be divided into two parts: dependent and independent. Again, independent sources can be of two types: voltage, current. Dependent sources can be of four types: voltage control voltage source, current control voltage source, voltage controlled current source, voltage, sorry, current controlled current source. So this is the basic like flow classification. Okay, sources can be broadly of two types: dependent, independent. Independent again can be of two types: voltage, current. Uh, Again, dependent sources can also be of four types. We'll discuss this one by one. Let us first concentrate on independent source, that is a independent voltage source. This one, independent voltage source. I have to remove this because okay, you are seeing that how a independent voltage source can is denoted. This one, V, using a V. The basic why independent, because uh, it establishes a constant voltage across two terminals. Let us say these two terminals are A and B. So across A and B, if this voltage source always keeps a constant potential difference or voltage difference, then it will be a independent voltage source. Again, further it can be divided two things. It can be divided into two things: ideal and practical. Okay, what is the difference between ideal independent voltage source and practical independent voltage source? Okay, the point is here. Let us okay. That means if you consider this voltage source, okay, there will be some circuit connected to it. Let us say some resistance, okay, some capacitance will be connected. It depends on okay, it's if DC voltage, then it's okay. But there can be different circuit elements. Let us okay, there can be different circuit elements. Now, I'm talking about independent voltage source that ideally what it should do if it is a voltage source of this much V or 5 volt, let us say. Okay, then across these two terminal, it should always produce a V volt or 5 volt. If this is the case, then it is a ideal voltage source. But in practical, this is not the case. This is not the case. What we are considering? We are considering that there is zero internal resistance, but in practically here in series to this voltage source, there will always be a internal resistance of the battery. If you see like any practical batteries, this internal resistance will be mentioned. Now, in the previous case, let us remove this capacitor. Let us remove this capacitor. Let us consider only a resistor. Let us consider only a resistor R. Forget about this internal resistance. Then what will be the current? What will be this current I? Again, current I will be equal to V voltage divided by the resistance R. Okay. Now we are considering that it is non-ideal. That means here there is a small resistance. Resistance or value, let us say R. Resistance of value Ri, the internal resistance Ri, internal resistance of the battery Ri. That's right. So now if you consider this small resistance Ri, then what will be the current? Current will be V divided by R. This R is already there. This R is already there. And in series, you are adding this Ri. So it will be R divided by Ri. So if it was the ideal voltage source where this Ri was equal to 0, then amount of current will be V by R. If you consider a practical voltage source where this Ri is not equal to 0, it has some finite value, then your current will be V divided by R plus Ri. So definitely, let us consider this I dash will be less than I, because in the denominator it has increased. Initially it was R, now it has become R plus Ri, and Ri is the internal resistance. It should be greater than 0, some greater than 0 value. So it cannot provide that much amount of current. Ideally, it should have provided V by R. Now it is providing V divided by R plus R. Okay, that is the main difference between ideal voltage source and a non-ideal or practical voltage source. In ideal voltage source, this Ri should be equal to zero. The internal resistance should be equal to zero. And in practical, it will have some finite internal resistance, Ri. Okay. So this is a independent voltage source. And again, independent voltage source we have seen of two types, that is uh, like practical and ideal. So this thing you have to remember till you are in this field of like electronics and electrical. Definitely you have to remember this always. Whatever circuit you make, you have to always remember this thing. What is the ideal internal resistance of a voltage source? Again, the same thing applies for current source also. So what is the independent current source? Again, if this is the current source, this is denoted by this is a voltage source, this is a current source. Again, there can be a resistance, load resistance RL. So what will happen? This current source will ensure that current I flows through this circuit. Okay. If it is a ideal independent current source, then it will ensure that always current I flows through the outside circuit. Okay, whatever elements is connected in series with this independent ideal current source, the current should always be I. If it's a current source of value I ampere. Now, what is written? It's written that the ideal for ideal current source, it has infinite resistance. Infinite resistance. So where this infinite resistance can be connected? It is connected always in parallel to the current source. Always in parallel to the current source. So ideally, it was I. When this internal Ri is tends to infinity. If it tends to infinity, then let us say I amount of current is flowing through here. I amount of current is flowing through here. If this resistance is infinity, that means it is nothing but a open circuit. This is nothing but a open circuit. It is nothing but open circuit because it has infinite resistance. So let us say the current I is being supplied by the current source. Here the current cannot flow because it is open circuit. The whole I amount of current will be flowing through this path. Okay, so if it is a ideal in independent current source, then the internal resistance which is connected in parallel to the current source, that internal resistance should be infinite. As a result, no current will flow through this path. The all the current that is being supplied by the current source will be flowing through this load resistance. Okay, so now if it is not the case, that means some finite amount of resistance is connected, then what will happen? Now, the I that was flowing through here, some part of it will be flowing through this. Let us say this is I dash. The rest, that means I minus I dash will be flowing, I minus I dash will be flowing through the outside circuit, that is to the RL. Okay, that will be okay. Now, that is a non ideal behavior. So, ideal current source has infinite resistance, internal resistance, and ideal voltage source has zero internal resistance. The reason you have already seen. Now, if you have any doubt in this internal resistance, this thing is very important. Why a current source has infinite internal resistance, and why the internal resistance of a voltage source we consider as zero. Okay. Now we are considering this V and I to be constant. It can also be a time varying, like AC source. We will come to this later. There it will be VT. That means the voltage will be dependent on time. The current will be IT. The current depends on time. Okay, current depends on time. you have any doubt here, please let me know in the chat. Otherwise, you can also unmute yourself and speak up. Okay. So these are the two types of, again, broadly, these are active elements, the sources that we are studying. These are active elements. Active elements can be broadly classified into independent and dependent. We are focusing on the independent first. Independent can also be of two types, voltage source and current source. Voltage source and current source both can be of two types, that is ideal and practical or non-ideal. Okay. So if there is a battery with a current source, then it would have no loss of power. I'm not able to understand, Ashutosh. If there is a battery with a current source, then it would have no loss of power. I'm not able to understand it. You can raise it later also, or you can clarify your question, or you can raise it later. Okay. As it has infinite internal resistance. We can have to see that how it is connected. We will encounter many circuits where there will be a voltage source, there will be current source at the same time. But then you have to see that how they are connected. Okay. Sir, by equating voltage across both the resistors of current source, can we find I? Sir, by equating voltage across both the resistor. Why will you equate the voltage across both the resistors of the current source? The current will see this thing that the, yes, it is a parallel connection. Yes, it is a parallel connection. But how you can, the current will be divided into two parts. Again, we'll see that current division rule, how it is getting divided into two parts, that we'll see. The current, total current I will be divided into two parts. How the current will be divided, that will be dependent on the resistance values. Higher the resistance, lesser will be the current. Higher the resistance, lesser will be the current. So resistance is not under your control. How internal resistance, it is like for a current source, it will be given to you. For a voltage source, the internal resistance will be mentioned. It is like the manufacturer's defect. Okay. RL will also be given. Being an engineer, you have to make a circuit so that the RL gets that much amount of power. So RL is not under your control. The internal resistance is not under your control. So you cannot make this. Okay. Current will be divided based on the ratio of the the ratio of the resistances, the load resistance and the internal resistance. Okay. So next is next we have discussed the independent sources. Next we will discuss dependent sources. So dependent sources, the first dependent source that we will discuss, V, V, C, V, S, voltage control voltage source. If you remember this diagram, you will never forget what is a voltage control voltage source. Okay. So this, how it is denoted? It is denoted by this diamond-like sign. All dependent sources are denoted by this diamond like sign. If it is a voltage source, that is dependent voltage source, inside the diamond there will be plus and minus. If it is a current source, inside this diamond it will be a arrow sign, whether in upside or downside, based on the in which direction current is flowing. But whenever is this diamond like sign, that will show the dependent sources. These both show dependent sources.
Recording in progress.
I forgot to start the record. So if this diamond, if you encounter diamond like symbols, then it will always be dependent source. Now inside the diamond where there is plus and minus sign, it will be a dependent voltage source. If it is only an arrow, it will be dependent current source. Now the first thing you see that okay, diamond sign is there, plus minus, definitely it will be a like voltage source. Definitely it will be a voltage source. Now it is controlled by what? That will be given by this, whatever is written beside it. See what is written beside it? Mu of VAB. Now mu, let us consider this to be some kind of a constant. We don't know what it is. After a few seconds, you will know what is this constant. Okay, but let us say that the value, that means this voltage across this is nothing but V of CD. Okay, so VCD is equal to V of AB. Okay, that means the voltage across this dependent source is dependent on VAB. VAB is the input. This is the input terminals. And mu is some kind of a constant. Now mu, what is mu? If you see this relation, VCD is equal to mu of VAB. Now mu, you can say that mu is equal to VCD divided by VAB. So this is output voltage divided by input voltage. Output voltage divided. So this mu denotes this voltage gain. That means how much increased value of output voltage you are getting for this much amount of input voltage. Okay. So this is the gain. Gain is if mu is greater than 1, then it is gain. If mu is less than 1, then it will be attenuation. Okay. That means the output voltage are reduced. Okay. So forget about this 4-terminal network and everything. This will come later. 2-port network and everything. This will come later. It is what it does. It establishes a voltage VCD between 2 points C and D. It establishes a voltage VCT between 2 points C and D in the circuit that is proportional to the voltage VAB between 2 points A and B. So if this is the voltage across these 2 points A and B, the output voltage VCT will be some constant, let us say mu multiplied by VAB. That means at the output you are getting a voltage that is equal to VCD, and it is controlled by the input voltage. It is controlled by the input voltage. So at the output you are getting this. So it is a voltage source, but it is being controlled by the voltage at the input. So it is a voltage control voltage source. Okay, VCVS. It is a voltage, but mu is now a voltage gain. Similarly, current control voltage source. 1 minute. Give me a minute. So next is current control voltage source. That means now see this, it is denoted by this. So definitely it is again a diamond like sign, and inside it is plus and minus. So diamond like sign, and inside it is plus and minus. So definitely it is a voltage source. Definitely it is a voltage source. But just outside, that means VCD, this becomes equal to VCD. VCD is equal to R multiplied by IB. And where IB should also be, if it is like a dependent sources, then the parameter on which it is dependent, that should also be shown in the circuit. So IB. So this voltage, output voltage is dependent on IB, and IB is shown here. IB is a current. Okay, current in the input port or input terminals. Okay, that means it is a voltage source. That means outside you are getting VCD, but it is being controlled by IAB. That means current. It's a current controlled voltage source. Now you can see that it is VCD is equal to R times I of AB, or R is equal to VCD divided by IAB. So voltage by current, this is nothing but ohm. This is nothing but ohm. That means is the mutual resistance between the mutual means between the input and output. That's why mutual. Then it is current controlled current source. See this one. Current control this one. Now you see diamond sign. That means definitely the source will be dependent, but inside it the arrow is given. So that means it is a current dependent current source. And just beside it, it is given as beta IB. So this is the current ICD. So ICD is equal to beta of IB. ICD is the current supplied by this dependent current source. But its value is dependent on beta times IAB. Where is IAB? Again, IAB is the current to the input terminals, input port. Okay. Now, so beta is, you can understand. So ICD is equal to beta times IAB. So beta is equal to ICD divided by IAB. That means the ratio between two currents. So here you can write this beta to be a current gain. It will have no like units, because it is the ratio between two parameters having the same unit. Okay, so it is unitless. Its gain is unitless. Similarly, the voltage gain is unitless. Now next is voltage controlled current source. Voltage, now current source, that means here if you see, it is again a diamond like sign with an arrow. So definitely it is a dependent current source. But beside it, it is given as this ICD is given as GMVAB. So GM is equal to ICD divided by V of AB. Okay, GM is equal to ICD divided by V of AB. Now V by I, you know it is resistance. I by V, it will be 1 by resistance, that means conductance. I by V, that will be conductance, opposite or reciprocal of inductance. So let me know if you have any doubt. This dependent source, independent source. If you have any doubt, please let me know. Okay, no doubt. Again, this will be used throughout. The example will do either today or tomorrow. There will be many examples based on these dependent sources. Okay. Today, the next class, that is our next class was tutorial, but since we have not started any like basic analysis tool or everything, that's why we are not doing the tutorial for this week. From the next week, we will do the tutorials. Okay, I will say share the tutorial sheet. You can just go through the problems and we'll solve those. Okay? But since we have not covered any significant amount of syllabus, it is impossible to do the tutorial. Okay, that's why today I will continue with the theory class. Okay, I will continue with the theory class. So these are the different. Okay, in chat. Uh, okay, can you explain? Can you explain what is in the circuit? Okay, that means you are seeing this. I am just removing everything. So the first thing you have to know that you are talking about like dependent sources. Okay, dependent source is always denoted using this diamond-like sign. If it is like circular, then it will be independent source. Inside it, there can be a arrow, there can be a sinusoidal signal. So these are all independent sources. For dependent source, instead of circle, you will always face this diamond-like shape. Okay, if there is a diamond like shape, the first thing you will conclude it is a dependent source. Now you have to look inside this diamond whether there is this plus and minus or whether there is this arrow. If plus and minus is there, then it will be a source. Okay, if in the inside the diamond side there will be plus and minus sign, then it will be a dependent voltage source. If inside this diamond sign there is this like arrow like symbol, it will be a dependent current source. Is it clear? Only this point, let me know. Asutosh, only this point, forget about the circuit first, only this point is clear. Yes, so this is clear. Now we are coming to the circuit. Now we are coming to the circuit because on what we are saying that is a dependent source, be it current or voltage. We are talking about dependent source. Now on what parameter it is dependent, to identify that you need some kind of a circuit. Because okay, this if you see this only this element, then you can say that it is a dependent voltage source. But now on what parameter is dependent, for that you have to see what is written beside it. This part you have to see. This part denotes what is the magnitude of the voltage. That magnitude is given as mu of VAB, and you already know that this is a voltage source. So at the output you are getting some voltage V, some output you are getting some voltage V. So this V will be equal to mu of VAB. Mu is a constant. We don't know what it is. Let us say some constant. So ideally it should be this V is proportional to VAB. If you remove the proportionality sign, then there will be some constant mu of VAB. Okay. Now, what does this mean? That means it is dependent on voltage. Which voltage? Voltage across AB. VAB. VAB is clearly given here. VAB is nothing but the potential difference across A and B. Okay, so the previous conclusion was it is a dependent voltage source. Now the new conclusion that you can do that, okay, it is dependent on some voltage. It is dependent on some voltage, dependent on some input voltage. So it will be a voltage controlled. It will be this voltage or this dependent source that will be controlled by this VAB. If VAB increases, this voltage will also increase. If VAB decreases, this voltage will also decrease. So this dependent voltage source will be controlled by the input voltage VAB. Okay, so that's why it is a voltage controlled voltage source. Now, is this first point clear, Asutosh? Then I will move to the next part. Yes. Okay. Second part. Second, here also see, again, one thing you can conclude that this is a dependent voltage source because the hexagonal sign is there and inside there is plus and minus. Okay, that means it is a dependent voltage source. Now, to find out on which parameter it is dependent on, you have to see what is written beside it. That means outside it is a voltage source, that is V or VCD, that is equal to R of IAB. Now, R is a parameter or constant. Now, will be R? What will the unit of R? R will be nothing but V divided by IAB. So it will be nothing but ohm. Or the resistance. Okay. So where is IAB? See, where is IAB? IAB is the current flowing through this input port. Okay. Between this A and B, what is the current flowing? That is IAB. That is coming from outside. Okay. So that's why this kind of a dependent voltage source is it is being controlled by the current source. So that's why current controlled voltage source. Is it clear? The second part, current controlled voltage source. Okay. Again, similarly, you can do the same thing. If it is a current source, you have to see whether it is a current controlled current source or voltage controlled current source. Based on that, the unit of the constant that will change, that you have to keep it in mind. These things you will again learn in your network analysis subject using two-port network. Now, these are the active elements that will be required. Okay, for basic circuit analysis, for DC circuit analysis. Okay. Next will be the resistance. That means a passive element. Okay. Three passive elements we'll learn: resistance, inductance, capacitance. Okay. So resistance, again, in the previous class we have discussed about charges. Charges can flow. Okay, charges can flow. If you give some kind of an outside force, okay, magnetic, electric field, anything, or chemical reactions, then what happened? It will attract or repel. It can either attract or repel the electrons. If you attract the electrons, that means the electrons that were there in the conductor, that will be moving out of through one of the terminals of the conductor, and it will be as a result, if these atoms, they are losing some electrons in their place, it will be devoid of electrons. That means some kind of a positive charge. So it was the charge for proton was balanced by charge of electron. You are losing electron, so amount of positive charge will increase. If you are getting excess electron from outside, then negative charge will increase. So that was the concept we discussed. If there is this flow of electrons, as a result, there will be flow of current. The resistance is the property of any material or any conductor which opposes the flow of the electric current through it. So it is the property due to which any conductor also will have some kind of a finite resistance. It will be very small resistance, but it will have some finite resistance. Yes. Okay. So the resistance is a property of a material due to which it opposes the flow of the electric current. A resistor is said to have a resistance of 1 ohm if the potential difference of 1 volt across the terminals causes a current of 1 ampere, simply by using Ohm's law. If there is a 1 ohm resistance and you are applying 1 volt across that particular resistance, then you will be getting 1 ampere current. Okay. On which factor it depends? Broadly, it depends on 3 factors, but temperature also becomes an important factor. Okay, that means resistance R depends on rho L by A. Rho is again dependent on the material, the resistivity of whatever material you are using to using as a conductor. L is the length of the conductor, and A is the cross sectional area. More is the length. If the length increases, then resistance will increase. If the cross sectional area increases, resistance will decrease. That means I'm talking about this type of a conductor. Okay, I'm talking about this type of this is the length L of the conductor, and here this is the cross sectional area. Okay, so it is directly proportional to the length, inversely proportional to the cross sectional area, and depends on the nature of the material. That means resistivity rho. So your resistance depend on rho L by A. Okay, it is rho L by A. What is the relation? If there is a voltage source, there is a resistance, there is a current, then it will follow Ohm's law. That means V equal to IR. Okay, so that is the basics of resistance. Resistance again is a linear element, and all those things apply here. So we'll now move to inductance. Okay, so you can take 5 minutes break. Okay, continuously 2 hours class will become burdensome. So you can take like 5 minutes break in between, like two whatever gap you get between two classes. Take that break, and we will return in exactly like 5 minutes. Like it is 4:05 now. We'll be again starting at 4:10. Okay. I will also drink some water and everything. Just take a break. Okay, for 5 minutes. Again, come back immediately after that 5 minutes at 4:10. Magnetic field. Okay, it stores energy in terms of magnetic field. So you know that if you consider any current carrying conductor, if you consider any current carrying conductor, current I is flowing, there will be some kind of a magnetic field. Okay, there will be some kind of magnetic field. Okay, now if you just make a coil of this like this, there will be now current is flowing. Okay, and there will be some kind of a magnetic field here. So this coil structure is such that the magnetic field that is produced, okay, magnetic field that is produced across this. So the magnetic field produced will try to oppose any change in the current. That means if some, let us say, I current is flowing, some current I is flowing, and let us say after some time the I is slowly increasing. So this magnetic field will be induced in such a way to oppose this di by dt. Okay, so how it will oppose? It will create a voltage. It will induce a voltage across this, let us say plus minus, so that it opposes this di by dt. If the current in the coil is increasing, the self-induced EMF or the EMF induced by this self-inductance, this inductance is also known as self-inductance. There is another called mutual inductance that will come in your network theory, or I don't know, or later also it may come. This what we are considering is self-inductance. So self-inductance, what the self-inductance will induce a EMF voltage V such that in a direction, so as to oppose the rise in the current, so the minus sign will be there. If you are talking only about the magnitude, so V will be equal to L di by dt. If you are talking about the sign, also minus sign. Okay, so there will be some kind of a source, let us say some source will be there, and there will be some L. So it will try to increase this voltage, so that let us say this is a V volt, this is small V volt. It will try to increase this or decrease this small V so as to resist the change in the current. Okay, it will resist di by dt, the change in the current over time. Okay, on what factor it depends? It depends on three things. Again, okay, number of turns, that is n, number of turns like this. These are the number of turns. So n number of turns, area of the cross section. Now again, if this is the inductor, if you see this inductor from like the side, this view, then it will look something like this, something like this. Okay, so this is the cross section. This is the cross section. So area of the cross section, length. Length is this length L. Cross section, for cross section you have to see it from the one side. Okay. So this, based on these three things, the inductance will be the value of the inductance you will get. So L will be equal to n squared A cross section area, and L is the length of the inductor. Mu is again a permeability. Again, if there is air, okay, in between these turns or coil, if there is air, if there is some kind of another like ferromagnetic material, okay, what will happen? So what is inside this inductor in the free space, that will decide what will be the value of mu or the permeability. N is the number of turns, A is the cross sectional area if you see from the side, and L is the length of the inductor. So in this way, you can find out what will be the inductance value. Okay. Now, what is current and voltage relationship? For resistance, you understood that it is V equal to IR. Okay. It is V equal to IR. But here, the voltage across the inductor is such that it opposes the change in the current di by dt. Let us consider only the magnitude, that is V is equal to L di by dt. Okay. Let us keep this di on one side and this V by L dt on the other side. So this dt we are bringing on this side, L also we are bringing on this side. Now we integrate over some time. Okay, let us see 0 to t. Let us see 0 to t. Okay, then you will be getting this kind of a relation between Vn. You can either represent in terms of this differentiation or integration. Okay, based on what kind of analysis you are doing, you can do either. That we'll see when we will use this to analyze circuit. Then we'll see. This is the current voltage relations. Now, what is the energy? I have the first line. I have told that this inductor. Okay, that will inductance also depend on thickness of the wire. Thickness of the wire. I don't think so. Thickness of the wire. Don't think so. Resistance will definitely uh, depend. R equal to rho L by A. In some way it will like affect. Okay, thickness of the wire will affect the cross section area and everything. In that way it will depend, but in straightforward way it will not. But again, the cross section area and everything will depend on the thickness of the wire. Okay, what is the cross section area, that will depend on the thickness of the wire, but directly it is not. Yes, in that way it will. In that way, I'm saying that thickness of the wire will somehow affect the cross sectional area, and that will affect the inductance. Okay, exactly we have to see that. Okay, thickness increases, then what will be the effect? But yeah, no direct relationship. But in that way, it will affect. Now, the first thing I have told you that inductance stores energy using kind of a magnetic field. Okay, so how much energy is stored? How much energy is stored for a particular, let us say, voltage that you are supplying? How much energy this inductor will store? So again, this is the relation, voltage and current relation. We are only considering the magnitude, V equal to L di by dt. Okay, and power we have already seen. Okay, what is power? Power we have seen, that is work done by time. This work done by time we have divided two parts: work divided by Q multiplied by Q by T. So work done to move a unit coulomb of charge, that was known as voltage multiplied by Q by T. We all know it is nothing but current. So power can be denoted by V multiplied by I. The same thing we are doing here. Power that is being dissipated, that is P equal to V multiplied by I. Okay. Instead of V, we can write this. Instead of V, we can write this. It is I multiplied by L di dt. So energy stored means, again, energy stored or work done, that is P multiplied by T. So P we have found, so multiplied by T. T will be of some amount duration, or T second, let us say. So in dt second, what will be the energy stored? That means dw. dw is nothing but P multiplied by dt. P we have already found, that is I L di by dt multiplied by dt. dt you can cancel it out. So dw, so dw is equal to I L di. I L di. Now when the current changes between these two values, it can be 0 and I we have considered, but it can be between any two values. Let us consider I is starting from 0. You have increased the current till some value I. Then you have to integrate it. That means this you have to integrate both sides. This, if you dw, if you integrate, let us say till 0 to w, then it will be w L, it will be I square by 2, and the upper and lower limit will be 0 till I. Okay, so this w will be equal to 1/2 L I square. So this much amount of energy will be stored. Okay, this much amount of energy. This L means the inductance value. This I means from zero, the current has increased till I. If the current has increased from zero to I level, then how much this energy is stored in this inductor, that is given by this formula. It will be very important in circuit analysis. W is equal to half Li square. Inductor stores energy in forms of magnetic field. So this is very important conclusion. Both this, both this and this conclusion for any kind of a circuit analysis. This formula is also important. V is equal to the magnitude L di by dt. This is also very important. And direction minus, in circuit you have to just draw the positive and negative polarity. Okay, so that is also very important for any kind of circuit analysis. We will see when we will learn some theorems, network theorems, and then we will try to apply these things. This will come later. L is equal to mu of n square A by L. This comes later, not in this subject. Uh, in network analysis, it will. Capacitance again stores energy in form of electric field. Okay, stores energy in terms of electric field. There will be plates, there will be charges that will be separated. That means there will be some kind of electric field E. As a result, the energy stored due to this electric field. Uh, okay, the capacitor will store charge in terms of this electric field. So, on what factor it depends? In fact, it depends on three things. Okay, see, parallel plate capacitor. Okay, again, what is the distance between these plates? Okay, if these plates you see in three dimension, this plate looks like this. Then what will be the cross sectional area A, and what is inside between these two plates? If it is air, if it is some kind of a dielectric material, based on this epsilon or permittivity will be selected based on what kind of a dielectric material is there in between the plates, what is the cross sectional area of the plates, what is the distance between the plates. Okay? Based on this, its capacitance will be determined. Okay, what is the relation? What is the relation between these? Okay, you know, Q is equal to CV. If you take the differentiation dq dt, C is a constant, capacitance constant, it is dV by dt, or dq by dt is nothing but current. So current will be C dV by dt. This is the relation between current and voltage. Okay. Now it is current in terms of voltage. How you can find voltage in terms of current? Again, you have to do the same thing. That means keep the dV on one side and I divided by C dt on the other hand. Now, if you integrate this, okay, if you integrate on both sides, you will get over some time t, you will be getting V is equal to I by C, okay, or it will be I will be a function of time, I will be a function of time dt and 0 to t plus some kind of a constant V0 initial voltage. So in this way, now you are getting the voltage in terms of current. Here current in terms of voltage, here voltage in terms of current, current in terms of voltage you are getting in differential form. Here you are getting in integration form. Okay, and this is the initial voltage V0. So this relation is very important. Okay, this and this, these two are very important relation for any kind of circuit analysis, and circuit analysis is what we will be concentrating on this subject. Okay. Power, energy stored in the capacitor is also very important. Again, energy is stored in the using the magnetic electric field here. Okay, so we will be starting from the basic. Again, power is nothing but V multiplied by I. Okay, and V let us keep this V constant, and I we have already seen in the previous case. I is nothing but C dV dt. So I is, instead of I we can write C dV dt. Okay, Let us say this amount of power is being dissipated per unit time. Now what will be the energy? Let us say dw, small amount of energy, okay, that is being stored when this much amount of power multiplied by small amount of time dt. Okay, work done is equal to power multiplied by time. We have we know energy is equal to power multiplied by time. We know this thing. So power is now vc dv dt, and this dt was there, so dt will get cancelled. Now dw will be equal to v capacitance dv. Okay, now we integrate both sides. It is 0 to w. It is now voltage is increasing. Voltage is, in the earlier case current was changing. Now here dv, that means voltage is changing. So definitely some, let us say starting from 0 volt, you are increasing the voltage till v. Okay, how you are increasing, that depends on many things, like you are giving a step input and everything, all those things are there that we'll analyze. But let us say you are starting from 0 volt and you are going till v volt. Then if you complete this integration, w will be equal to c is constant, that is come outside, v square by 2, okay, and 0 to v, so it will be half c v square. So this will be the energy stored, this will be the energy stored. Okay, this energy stored is also very important. The basic relationship between I and V in terms of both differentiation and also in terms of integration. Both you need to be clear. And then the energy stored. Energy questions will be asked on energy stored also. How much energy is stored? Okay. Okay. So these are the, again, basic elements. Types of what is the difference between circuit and network? This I will share. This whole slide I will share, starting from this slide. Okay. This you will get today only. I will at the end of this class I will create a Google Classroom. Here, there and there you will join, and yes, that also you can make using like just removing the C and everything. This also you can get. Okay. And half CV squared is standard. You can make further modifications just by including the exact definition of C and everything that you can. Okay. So these slides you will get today either by mail or by Google Classroom. Okay. Yes. Board of the laptop, there will be like a complex circuit. How to analyze those kind of complex circuits? Using some basic theorems, network theorems, you will be able to like analyze any kind of complex circuit. That is the main aim in the next few sessions, right? Give you the idea of the basic theorem so that you will be able to analyze any kind of circuit. So before going into network theorems, we have to know two basic laws, KCL and KVL. We have already done this, but again, there is this problem of what sign you take and everything. So we'll learn from the basics. I will use a sign convention. You can use on your own convention, whatever you have learned till now, but you have to see that you do it correctly. Whatever convention you use, you do not mix two conventions. Okay, whatever convention you use the same throughout solving this problem. Okay, don't mix and match. Okay. So what you are seeing here, whether it is a network or a circuit, please let me know. Some kind of a thing you are seeing here. Okay, whether it is a network or a circuit. Whether it is a network or a circuit. Yes. A proportional circuit, yes. So there is closed path through which current can flow. There is a closed path through which this current can flow. If you see this current I1, there's a closed path. These are closed paths are there. So if it's a closed path, definitely the interconnection some elements. So definitely it is a network. It is also a network. It is also a circuit. Network. What is the requirement of network? That is interconnection of two or more elements. So here you can see that this resistance of 12 ohm is interconnected with this 8 ohm resistance. It is interconnected with this 5 ohm resistance, and it is creating some kind of this. Now we will see what it is. The next point. But so definitely it is a network, but it has also some closed path for at least one closed path. So definitely it is a circuit and both are network also. Okay? Now consider the electric circuit below. In this circuit, there is a current source, resistances, nodes, branches, loops. Okay. Now many new terms we have introduced. Current source, you know, it can be either a dependent source, independent source, that you have to see the circuit. Here you can see it is a again a circle. It is not a like a diamond shape. So it is not a dependent source. It is a independent source circle, and inside the circle there is no plus minus sign. There is a arrow sign. So definitely it is a current source. Okay. Resistances. We have already learned about these passive elements resistances. What is unknown is nodes, branches, and loop. Okay. Nodes, branches, and loop. What is nodes? I have written here. That means it is the interconnection of at least two or more than two elements. If you see, this you will get as a comment I have written meeting point of two or more elements, or the junction or interconnection of two or more elements. The elements can be passive, active, anything, but is a meeting point of two or more elements. It is called a node. Very important node. Branches in between two nodes, the path between two nodes, the circuit between two nodes, that is known as a branch. The path with again in this path there can be other elements also. Between two nodes there can be a resistance. Here see, it is a node. It is a node because it is the interconnection of this element, this element, this element. So this is a node. B is a node. A is also a node. In between this A and B node are interconnected with each other using some kind of a path. That path also has a resistance. This path is known as a branch. That means if you see the definition, the path between two nodes is called a branch. A branch may have one or more elements. A branch may have one or more. What is a loop? Loop is again any closed path. Again, so here, if you can see this, this is a loop. This is again a loop. This is again a loop. This is again a loop. It is providing a closed path for the current to flow. Again, this is another loop. More than that, this I'm not able to write here. Okay. So what you are seeing, what is the loop? Okay, what the circuit that you are seeing is looks like this. So this is 3 ohm, this is 6 ohm, this is 2 ohm, this is 13.7 ampere, this is 5 ohm, this is 8 ohm, this is 12 ohm. Okay, so this is this thing. This is a loop. This is a loop. This is again a loop, closed path. Further, this is also a loop. 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 So these are all loops. These are all closed paths. Then what is the difference? Another concept is their mesh. There's two very related concepts: mesh and loop. Loop is any closed path. That is, through that path, current can flow. Any closed path. What is mesh? Closed path with no other closed path inside it. There is a closed path, but there is no other closed path inside this. So if you see now, if you see the outside closed path, so this is also a closed path, but inside it, this is there, inside it, this is there. So the outside loop is, it is a loop, it is not a mesh. But here, see this is a mesh because there is no loop inside it. There is no closed path inside it. Again, this is a mesh because there is no closed path inside it. I will again ask this concept. Okay, I will take name. I will ask this concept tomorrow. Okay, when we will do mesh analysis, I will ask you this concept. Okay, I will ask you this concept. Similarly, this is a loop. This is a loop, but this is a mesh because inside this loop there is no other closed path. This is a mesh because inside it there is no other closed path. Okay, so this is a basic difference between loop and mesh. Loop is any closed path. Mesh is a closed path with no other closed path inside it. So this circuit is given to you. You have to answer. Now you have to answer how many nodes are there, how many branches are there, how many loops are there, how many meshes are there. So for this given circuit, you have to count. I need answers from all of you. Okay, everybody has to write and write it personally. Don't write in the chat. You can write it personally. Okay, send personal messages to me. Don't write it. Don't leave. I have not taken the attendance. You will get attendance for both the classes. Okay, don't write it. Send direct message, not in the general chat. So what you have to find, you can see this circuit. You can see this circuit. You have to find out how many number of nodes are there, how many number of branches are there, how many number of loops are there, how many number of meshes are there for this circuit. Okay, and how many mesh branch, how many branch are in, how many branch? Everybody, there are 9 students. Okay, 9 of you are there till now. So I need personal messages, direct messages from all of you. Arin, you have mentioned three things, but how many number of branches? Okay, Asutosh is saying both Asutosh and Arin. Nodes, please see carefully. Nodes, you are saying some number, but is it correct? I am not talking about maze and loops. Forget about that. The first thing is nodes. See whether you are correctly writing the number of nodes or not. All of you first write the number of nodes. Carefully see. It should be unique nodes. It should not be repeated. First, everybody write how many number of nodes are there in this circuit. No, nodes you are not. You are making the answers are wrong. How many number of nodes? Okay, Shreya has said something, but again I will ask you, Shreya, to again see whether you have written it correctly or not. Carefully see. I have told you that nodes should be like interconnection of two or more elements, but you have to also see what is the difference between 2 points. You have to also see what is the difference between like 2 points. Okay. In one way, okay, in one way you are correct. Going by the basic definition, you are correct. Yeah. But while analyzing, you will see that okay, that many number of nodes are not there. And the number of unique nodes are because no, four nodes are there. Because here, this is not a unique node. Okay, there is no element here. So this is like a combined node. All these nodes that you are seeing in the like bottom part, these are all like a clubbed together. It can be clubbed together as a single node B, because there is no element in between. Here there is no element. Here there is no element. So you can club this. So how many number of unique nodes? A, B, C, D. Okay. By basic definition, you can say okay, there is an interconnection of this area. But here there are no elements. You can see. Can you call this a node? Okay. Can you call this as a node? Because okay, some element is there. Source is there. Resistance. So this branch has some element. There is no element here. There is no element here. So there is no interconnection of two or more elements. Here also. Here you can say okay, this is a node. This is a node. There is an interconnection of two elements. Okay, but this and this you can just merge. This and this you can just merge. Okay, this is not a unique thing. This B is not a unique. You can merge all these things. This will become a single node. A and C. How A and C should be same? Yes, A and C is also same. You can club this together. You can club this together. But A and C are separately two nodes, because in C you can say that okay, it is an interconnection of this element and this element, two or more. It is an interconnection of two elements. Again, A, it is an interconnection of these two elements. Okay. B, it is an interconnection of 12 ohm resistance, 8 ohm resistance, 5 ohm resistance. Again, this point also you can say that it is an interconnection of 12 ohm resistance, 8 ohm resistance. Here it is an interconnection of 6 and 3, but here it is a not an interconnection, it is a single element. So this is a node, this is a node, but this you can merge. Okay, this A, B and C are separately nodes. Okay, A, B and C, sorry, A, this will be D, this will be D, A, B, C and D. Okay, but this you can also consider as two nodes, because here also there is a one node, here also there is a one node, but later it will be like a single node. Okay, but C definitely should be a node. One was A and C should be same. No, A and cannot be same, because A is, you can club this together, definitely you can club this together, but A is separately node because it's the interconnection of two, it is interconnection of two. And this will be clubbed together while doing like analysis, this will be clubbed together. Okay? But by going the basic definition of node, you can identify these things. It should be a interconnection of two or more uh, elements. Okay? Branches. If you have identified the nodes, then unique paths between two things, two nodes will be the branch. Number of loops. Now tell me how many number of loops. First tell me how many number of mesh. Then tell me how many number of loops. Three loop. No, Akash. Then you have to. It is wrong. See, loops, I have told you that at any closed path. Loop, the basic definition of loop is any closed path. Now from that definition, see how many number of loops can be there. Any closed path. So this can be a loop. Sorry, this can be a loop. 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 So four loops I can see, and these are also meshes, because there is no closed path. There is a closed path, but inside it there is no closed path. So these are four meshes. One, two, three, four. Four meshes will be there. Meshes are also loops, so four loops will also be there. But there will be some additional loops. That means if you take this loop, then there is a closed path, but inside it there are two more closed paths. Okay, but it is a loop. So 4 plus 1, 5. Okay, again this 5 plus 1, 6. This one again 6 plus 1, 7. The outermost 6 plus 1, 7. Then this one 7 plus 1, 8. 7 plus 1, 8. 7 plus 8 plus 1, 9. 8 plus 1, 9. Now if you take this one, then it will be the same loop. So 9 loops. Okay, 9 loops plus again if you take this loop, it will be 10. 9 plus 1, 10. I don't know whether I am missing or not. So in this way you have to identify the loops. Loops can be any closed path. You have to see all the combination. Outside loop, inside, taking two mesh, you can create a loop. In this way there can be various combination of loops. You have to see all those. Okay, mesh, it's very easy. There will be no closed path. So this is a mesh, mesh 1, mesh 2, mesh 3, mesh 4. Okay. Yeah. So this will be very important thing. Identify number of nodes. You have to like wherever there is no unique element, you have to club those things. Later we will see why we will be clubbing two nodes. That will be important thing to reduce the number of variables, to reduce the number of to reduce the computational complexity. We will identify those things. So nodes, identifying the nodes, branches, loops, mesh, very important. Nodal analysis, mesh analysis. In nodal analysis, you have to identify unique nodes. In mesh analysis, you have to identify unique mesh. There are formulas to calculate it, but by seeing also the circuit, you should be able to identify this. Okay. Yes. So yes, we will stop here. Okay, I will send the slides till this part. From tomorrow, we will start the sign convention, KCL, KVL. You just go through all the slides. If you have any doubt, please let me know. Okay. In the meantime, I will stop the sharing the screen. I will create a Google Classroom, and I will create a classroom, and you have to join it there. I will share the link. You have to join. New class, create class. It will be